Okay, let's take a look at these, see how we're doing so far. So each of these you're asked to evaluate. And when you're asked to evaluate, that means you're given a formula and then you're given numbers for the variables or the letters in that formula. So you need to replace the letters with the numbers and then proceed with your order of operation. So the first one here, m equals q times 3g minus p. So we're going to evaluate that to find the value of m when q is 7. So 7 times parentheses 3g. Well, g is 8, so that becomes 3 times 8. Remember, 3g really means 3 times g. A number in front of a letter means multiplication. Minus p is 11, so we put 11 in there. Now our order of operation tells us we have to work inside the parentheses first. In there, we're going to multiply. 3 times 8 is 24. Next, we're still inside the parentheses. We have the 24 minus 11, which is 13. And we're down to a single number in the parentheses, so we can take the parentheses out, but we have to recognize these parentheses are also signifying multiplication. And then finally, all we have left is the 7 times 13, which is 91. So m equals 91 is what we get when we evaluate that expression. Number 2, f equals 4p plus n over d. So 4p, well, p is 6, so 4p becomes 4 times 6, plus n is 8, over d is 4. Now remember, this fraction bar means we have to get the top down to a single value, the bottom down to a single value, and then divide. Well, the bottom's already a single value, so we just have to calculate the top out. So 4 times 6 plus 8. 4 times 6 has to happen first. That's 24. And 24 plus 8 is 32. That's 32 on top, divided by 4 on bottom. We divide that out, we get 8. So f equals 8. Any questions there? Okay. Well, today we are wrapping up Unit 1. So a couple of comments I want to make. First of all, make sure you check the grade book in Blackboard. Most of you have submitted both quizzes so far, but there were a couple of quizzes that could not be downloaded or could not be opened in Blackboard. It just kept giving me an error every time I tried to open them. So if you have either no grade or a 0.1 for a grade, that means your quiz wouldn't open. That means you'll have to email your quiz to me, resubmit it to me so that I can grade it and get that in the book for you. Otherwise, having a 0 on a quiz really does hurt your grade in the long run. It takes a lot to come back from that. So, and I know if you submitted something, I know you did the quiz, and I'd really like to see you get the points for your effort. So make sure you do that when you get a chance. Next, also reminder, Unit 1 test is tomorrow. What is that, September 9th? Yes, it is. The way I'm going to do that is I'm going to have it available on Blackboard all day. You may use your notes, your book, calculator. So basically, you can use any resource you have, other than you can't sit down with your buddies and work on it together. Sometime during the day tomorrow, it'll be open from 12:01 a.m. to 11:59 p.m. tomorrow. Sometime in there, you have to download it, complete it, and submit it. And I will get those graded in the book for you, hopefully by class time on Thursday. If not, I will have them graded by next week for you. So class on tomorrow. Will be dedicated to the test. Now, this first test is not that bad. A lot of people will finish it up in 20 to 30 minutes, but I still give you the full class period for it. If you want to come in the classroom, if you have a laptop that you can use or whatever, and you want to come into the classroom and work on it in the classroom, you're welcome to. I will log in. I will be online for you to have any questions. Or if you want to work on it, elsewhere and just submit it during the day, there will be no required classroom activities tomorrow. So if you go somewhere else and work on the test, you're not going to be, marked down for not being in the classroom. The biggest thing is as long as that test is done by 11:59 p.m. tomorrow. Okay, well then, anybody have any questions on how the test is going to work or what they need to do for the test? It'll be just like the quizzes. You download it, complete it, load it back in. Okay, then let's go ahead and wrap up our last topic here then for Unit 1. And we're going to talk about first part of it is something called divisibility. Divisibility, that means that it divides without remainder. Now, there are a lot of other ways you could state that. You could say it divides and gets a whole number answer, or whatever. It divides without a fraction or decimal. Means the same thing. So if I say that 20 is divisible by 4, well, that's because 20 divided by 4 equals 5. 5 is a whole number. There's no remainder, no decimal, no fraction. Now, numbers that are divisible, or the numbers that a number is divisible by, those numbers that divide a number, are called factors. So 20 we said 20 could be divisible by 4, but it could also be divisible by 2, has the 4, the 5, and the 10. Those are all numbers that divide 20. Those are the factors of 20. Now you might say, well, 20 divides by 1. That gives us 20. There's no decimal or fraction or remainder there. It also divides by 20, which would give us 1. There's no decimal, fraction, or remainder there. When we talk about factors and divisibility, we exclude 1 and the number. Because every number can be divided by itself, and every number can be divided by 1. So we leave those out because those are not terribly useful. Also, some of the other things we do with these factors, using 1 or the number itself wouldn't work real well. Well, factors come in pairs. So again, using 20, the factor pairs would be 2 times 10 or 4 times 5. If you really wanted to get technical, you could do negative 2 times negative 10, because a negative times a negative is a positive, and negative 4 times negative 5. We're going to stay positive here today. So if I ask you to factor 20, how would you know which one of these factor pairs to give? Well, in most cases, you won't. If you get into a more advanced algebra looking at factoring algebraic expressions, you would have to consider all those pairs and pick out the one that fits the rest of the problem. But we're not getting into that. We're just factoring the numbers. So most of the time, rather than just saying factor, when we're told to factor, what they're really asking us to do is prime factor. And what prime factor is really saying is break it down into the smallest possible numbers that multiply up to make that number. So for 20, we use something called a factor tree, where we start with our number and we branch it off. We find any number that divides 20. Well, 20 ends in 0, so we know it's divisible by 10. So we divide it by 10. We're left with 2. 10 can be divided further. 10 can be divided by 2, giving us 2, or 2 and 10 divided by 2, would leave me with 5. None of these numbers can be divided any further, 2, 5, and 2. So those are what we would call the prime factors. These are what we call prime numbers. What are prime numbers? Prime numbers are numbers that have no smaller factors. For 2, there's nothing smaller than 2 that we can multiply together to make 2. Same for 5. Those are prime numbers. 20 is what we refer to as a composite number. It has smaller factors. If you get into machining or metallurgy, you talk about composite materials. Composite materials have smaller components to it. Ceramet is a big one in machining. It's actually made of a mixture of metals and ceramics. It's composed of other smaller materials. So we prime factored 20 here. We got 2, 5, and 2. Let's put them in order from smallest to largest. That's 2, 2, and 5. Notice I put multiplication between them because that truly is what it is. If I did 2 times 2 is 4 times 5 is 20, they multiply, those prime factors will multiply up to give us the number that we factored. Now, as I was factoring that, you heard me say, well, 20 is divisible by 2 or by 10. How do I know that? Well, there are some shortcuts we have called divisibility rules. Some of these are pretty useful, some of them are not. Let's take a look at all of them. How do we know if something's divisible by 2? Well, we usually say, well, if the number's even. Well, what does even mean? That means the last digit is 0, 2, 4, 6, or 8. So if I have the number 734,000, oh, what is that now? 520. That ends in a 0, which means it's an even number. This is divisible by 2. Well, how do I know if something's divisible by 3? We use the sum of the digits. This is a rule I found especially useful because there are a lot of numbers out there that you don't think can be divided by anything, but you add up the digits and it's divisible by 3. So what do I mean by the sum of the digits? That means I take each of the digits here and I add them up. So I'm going to do 7 plus 3 is 10, plus 4 is 14, plus 5 is 19, plus 2 is 21, plus 0 is still 21. So those digits add up to 21. Is 21 divisible by 3? Well, sure it is. In fact, if I'm not sure, I can go to the next step. I can do 2 plus 1 is 3. That's definitely divisible by 3. So 21 is divisible by 3. 734,520 is divisible by 3. Tell if something's divisible by 4. This rule is a little bit trickier. I'm going to put it out there, but it's one that I don't actually use. Because if something's divisible by 4, if I divide by 2 twice, I've divided by a 4. So I just use the one for 2, and I don't even try to worry about 4. But the way the divisible rule for 4 is if the last 2 digits are divisible by 4, then the whole number is. So what does that mean? Well, that means if I looked at the last 2 digits here is 20. Is 20 divisible by 4? Yes, it is. Now the problem with that rule, that looks like it worked really easy there, but the problem for that rule to work is you'd have to memorize all of the multiples of 4 from 0 to 100. And if I asked you, well, is 86, is that a multiple of 4? Is that divisible by 4? I wouldn't expect you to know that off the top of your head. It's not, by the way, for those of you that were wondering. 5 is a lot simpler. Last digit is 0 or 5. Well, for our 734,520, that last digit is 0. That is definitely divisible by 5. 6. 6 is another one that actually isn't bad, but if I need to divide, if I can divide 6 out of something, if I divide by 2 and then divide by 3, I've divided by 6, really. In fact, that's the rule for 6. If it's divisible by both 2 and 3, then it's divisible by 6. Well, this number up here is 734,520. It was divisible by 2 and it was divisible by 3, so it is divisible by 6. 7. There actually is a rule for 7, but it doesn't work for every number. It only works for certain numbers, for really huge numbers with a lot of digits, or numbers where the last digit's pretty small. Let me just give you an example of it rather than trying to write out how the rule actually works. So for example, 343 is divisible by 7. The divisibility rule for 7 is you take the last digit and you double it. 3 times 2 is 6. Then you subtract that from the remaining digits. Well, the remaining digits up here are the 34. So 34, not 36, 34 minus that 6 is 28. If this result here you get when you subtract is divisible by 7, 28 is divisible by 7, then the whole number is divisible by 7. Well, there's 2 problems there. That only works for certain numbers. I can't take the 28 and I can't apply this rule to the 28 because if I double 8, I get 16. Can't subtract that from the 2. So it doesn't work for really small numbers. It only works for really large numbers, or numbers that have really small last digits. So it doesn't work for every number, and it's really kind of a pain. Because if there's a 5 or 6 digit number up there, I'm still looking at a 4 or 5 digit number trying to determine if it's divisible by 7. Not really something I want to do. I could keep going with it if I wanted to, I suppose, but that gets to be a lot of work. So the divisibility rule for 7 is not horribly useful. So for the most part, we're just going to, since we have calculators, just punch the number in your calculator, divide by 7, and see if there's a decimal on it. For 8, similar to the 4, the rule for 8 is there, but it requires you to memorize a lot of multiples. The rule for 8 goes off the last 3 digits. If the last 3 digits of a number is divisible by 8, the whole number is divisible by 8. So up here, last 3 digits is 520. 520 is actually is divisible by 8. Gives us 65. So since 520 is divisible by 8, this whole number is divisible by 8. Nine. Well, similar to the 3s, 9 goes off of the sum of the digits. For this number up here, we said the digits added up to 21. Now we're dividing by 9, not 3. 21 is not divisible by 9. This number up here is not divisible by 9 because the sum of its digits is not divisible by 9. And finally, we have 10. Of course, to tell if something's divisible by 10, it just ends with a 0. The last digit is 0. There are more divisibility rules as we go up the line. Unfortunately, they're similar to the divisibility rule for 7. They get more and more complex as we go. Now, those rules, the more complex ones, actually, unlike the 7, will apply to every number. But the amount of work you put into the divisibility rule is really less work than it would take just to punch it in the calculator and see if it divides out. I'll give you an example. Like 11. Divisibility rule for 11. What do I have there? So 753,291. If I want to see if that's divisible by 11, I start with the first digit, and I take every other digit after that. And I add those together. 7 plus 3 plus 9 is 19. Then I take the remaining digits, and I add those together. 5 plus 2 plus 1 is 8. Then I subtract the largest one minus the smallest one. 19 minus 8 is 11. If that result is either 0 or divisible by 11, then the whole number is divisible by 11. Well, since that number is 11, that's definitely divisible by itself. This whole number is divisible by 11. Again, you can see that rule is kind of complex. And it'd be much easier just to punch it in the calculator. 753,291 divided by 11. Hey, I don't get a decimal, so that's definitely divisible by 11. That'd be way easier. So let's look at prime factoring here. Do some more examples. I'm going to have you prime factor. Oh, let's see here. Prime factor 210. So I'm going to do my factor tree. What I usually do is when I'm trying to prime factor something, I look for 10 first, then 5, then 2, and then 3. The reason I look for 10s and 5s first is they're real easy to spot. The number ends in a 0 or a 5. 2 is also fairly easy. It's an even number. 3 is a little bit more work, so that's why I hold off on that. Well, for this number here, the 210, it ends in a 0, so I know it's divisible by 10. So I put 10 on one branch here. On the other branch, this number has to multiply with the 10 to make the 210. The way I find that is I just do 210 divided by 10 is 21. So notice these two multiply up to make the 210. Two branches have to multiply up to make what they branch from. Now the 10 will be split up. It's divisible by 2. 10 divided by 2 would leave me with 5. Those are both prime, so I'm going to circle them so that I know we are done with those. Moving over to the 21, not divisible by 5, not divisible by 2, but it is divisible by 3. 2 plus 1 is 3. If I divide by 3, 21 divided by 3 is 7. Well, 3 is prime, no smaller factors for 3. 7 is also prime. So let's put these in order. From smallest to largest, 21 is 2 times 3 times 5 times 7. So 210 has factors of 2 times 3 times 5 times 7. If I multiply those up, I will get 21. Let's do another example. Let's prime factor 36. So I'll put 36 over here. Not divisible by 10. It's not divisible by 5, but it is even, so it's divisible by 2. So I put 2 on the left side. 36 divided by 2 is 18. Now the 2 is prime, so I'm going to circle it. 18 is also even. It's divisible by 2. 18 divided by 2 is 9. The 2 is prime, so I circle it. 9 can't be divided by 2 anymore, but it can be divided by 3. 9 divided by 3 leaves me with 3. Both of those are prime. So 36 prime factors to 2 times 2 times 3 times 3. That, by the way, could be written, they have something called exponential form. But rather than writing out as 2 times 2 times 3 times 3, it's 2 squared times 3 squared. Either one of those forms is okay by me. I actually prefer the top one. Well, why are we concerned about prime factoring? It sounds like quite a jump from the working with whole numbers that we've done so far. Well, prime factoring is the key to a lot of things, and our next unit is going to be on fractions. We're going to use a lot of those things in fractions. Let's look at common factors. If I give you two numbers and I ask for the common factors, let's ask for the common factors of 12 and 18. I would do my factor tree for 12. 12 is divisible by 2, leaving me with 6. 6 is divisible by 2, leaving me with 3. So 12 is 2 times 2 times 3. 18, it's even, so it's divisible by 2, leaving me with 9. 9 is divisible by 3, leaving me with 3. So 18 is 2 times 3 times 3. 12 and 18 have several common factors. They both have 2's. They both have 3's. They actually have larger factors that are not prime, like 6. I guess 6 is the only larger one. But since there are several common factors in most cases, what we are concerned with is the greatest common factor. So the 12 and 18 have common prime factors of 2 and 3. But a non-prime factor that they would both have would be 6. The largest of those factors is the 6. Well, how do I find that greatest common factor? Well, it's actually fairly simple. We take all of the common prime factors. It's the product of all common prime factors. So I have common prime factors of 2 and 3. 2 times 3 makes 6. 6 is the greatest common factor of 12 and 18. So find the greatest common factor of, let's do 45 and 75. Well, if I were to do the factor tree for 45, I would get 3 times 3 times 5. If I did the factor tree for 75, I get 3 times 5 times 5. What do they have in common? They have a 3 and they have a 5. 3 times 5 is 15. 15 is the greatest common factor of 45 and 75. It is the largest number that divides both. "45 divided by 15 is 3. 75 divided by 15 is 5. There's no larger number that divides into both of them that both of them are divisible by. Let's talk a little bit about multiples. If I give you the number 6, multiples of 6, well, the first one is just 6. It's 6 times 1. The next one would be 6 times 2, which is 12. 6 times 3, which is 18. 6 times 4, which is 24. 6 times 5, which is 30. 6 times 6 is 36. And as you can see, this list can go on forever. Multiples are all of the numbers that this number divides. The multiples of 6 is every number that 6 divides. That's divisible by 6. In other words, I can count up by 6. Multiples themselves are not nearly as useful as something called common multiples. Let's say I have 6 and 8. Well, my multiples of 6 are 6, 12, 18, 24, 30, 36, 42, 48, 54, 60, and of course they keep on going. For 8, 16, 24, 32, 40, 48, 56, 4, 72, 80, and of course keep on going. Well, we can see here already in this list, we have 24 that's a common multiple and 48 that's a common multiple. If we kept going, 72 is actually also a common multiple. Common multiples are multiples of both. Now, again, there's going to be an infinite number of common multiples. I'm not concerned with all of them. What we're typically concerned with is something called the least common multiple. Least means the smallest. For the 6 and 8, the smallest one is 24. So the least common multiple of 6 and 8 is 24. That's the smallest number that both 6 and 8 divide. They're the smallest number that's divisible by both 6 and 8. Find the LCM of 4 and 6. I can list out all those multiples until I find one that's in common, or I can use my factoring. If I use factor trees, 4 is 2 times 2. 6 is 2 times 3. To find the least common multiple, I look at the factors that are the same. They both have a 2. I'm not worried about those for now. They're the same, so I don't have to worry about them. But the least common multiple, or any common multiple, has all the same factors. So now I look at the factors that are not in common here, not the same. The top number, the 4, has a 2. So in order to make them the same, I multiply the 6 by 2. Now the 6 has all of the factors that the 4 has. Now I look at the 6. It has a 3 that the 4 doesn't. So I multiply the 4 by a 3. Now the 4, oops, that should be a 3. Now the 4 has all the same factors that the 6 does. 2 times 2 is 4, times 3 is 12. 2 times 3 is 6, times 2 is 12. 12 is the least common multiple of those numbers. Now I realized we blew through that process pretty quickly today, but that's one of the processes that can be used for finding least common multiples. And of course, when we look at fractions, starting Thursday, least common multiples is the same process we use for finding the least common denominator. And greatest common factor is what we're looking for when we go to reduce a fraction. So we're going to use those processes, being able to use the factors to find those numbers. Many of us will get to where we can just look at the number and we just know it. We've worked with the numbers enough that you can look at them. You can look at 4 and 6 and say, yep, they both go into 12. Let's use 12. But if you do get larger numbers or numbers you're not as familiar with, you can use the factoring to figure that out. Okay, I've been a little stingy on giving you homework time at the end of class, so I wanted to give you a little bit today. So your homework today is page 26 in the book. Numbers 1 through 63, the odds. So I will warn you right now, the factoring problems on the test are ones that the highest number of students get wrong every year. So make sure you do a few of these and make sure you're good at very least doing the factor tree to do the prime factoring. That's really the part that we are concerned about here at this point, is that you're capable of doing the prime factoring. Okay, I'll let you guys have a few minutes here to get started on the homework if you want. Otherwise, if you want to get to cleaning up wiping down your table and get moving, I understand that as well.